that you're talking about, isn't the ordering still within an octahedral sites?
Yes, in octahedral, but on the 420 planes that cut the octahedral sites,
yes. No,
with a lot of them being empty.
Right, this is not just, see, I am creating in a sense a fictitious system, although it is not totally fictitious, because you'll hear a talk Thursday morning by Sam Myers where palladium D, actually something like 1.3, has been studied through ion implantation techniques. But since I am using a system where all the octahedral sites in the first instance are occupied, and then extra ones are going into the tetrahedral sites, I'm not going to see any ordering among the octahedral sites, which are going to occur only if there are vacancies there to begin with.
One very simple way of accounting for quantum effects in your calculation and estimating fusion rates would be to calculate the semi-classical tunneling integral for each DD pair as it comes to the distance of closest approach. I think when you do that, you'll find that the very improbable distances, which are small, become much more important, but I think would not be enough to boost the rates up very high.
I guess I didn't fully understand that, because, you see, in no case do I get them any closer together than in a molecule.
That's correct.
And,
but then what you should do is imagine moving them together while freezing everybody else and calculating the integral that we saw this morning of square root of v minus e, and then exponentiating it. You should be able to do that.
Oh yes, I guess I'd be more enthused about doing it if I saw distances down the order of 4/10 of an angstrom, something like that.
So would I, but...
Pants and Westinghouse. Approach distances of 1.3 angstroms have been observed with diffuse neutron scattering peaks. And I have a question, would you care to model a glassy system and look at a radial distribution curve for that in order to get closer approaches?
That certainly might be of interest. People have done, of course, quite a bit of modeling of glasses, but not of the palladium hydrogen system that I'm aware of.
Do you think, is there a possibility of getting it close if you could get the palladium into a glass?
That's not immediately obvious to me that they would get any closer. I mean, the thing that's limiting you here is simply this Coulomb repulsion and the screening length. And so it's just very difficult to see how rearranging the palladiums, which in a sense is what you're doing with the glass, is going to shorten that screening length significantly, unless you can somehow or other boost up the electron density enormously, which I don't believe at least happens in glass.
Since deuterium atoms recombine at the surface to form D2, it would seem then from your result that the closest approach is at the surface. Can you think of any potentials that would be perhaps enhanced to cause tunneling or other phenomena that we haven't looked for at the surface?
I have not considered surface phenomena at all, so I guess I'd rather not comment on that. But I fully agree with your basic statement that in the whole scenario of all these experiments, it appears that the closest the deuterons are together is when that recombination has taken place.
James Aird at Naval Research. You can use many body potentials, like embedded atom potentials, which I guess were developed at Sandia to do the same work. And they'll treat surfaces and they'll treat some electron screening effects also. And in fact, we've done that at Naval Research and found the same results you did with pair potentials. They don't get very close at all. And the potentials we have are good for surfaces also, and even there, you don't get close.
Tajima, University of Texas. Do you have electrolysis effect? That is, that the ions, deuterons are superionic conducting, and or similar character exhibiting in your simulation? Well, or it's only in the sitting in the equilibrium? I think that they are different conditions.
Well, you see, this is one thing that's nice about the molecular dynamics simulation is that the atoms do what they want to do, given the potential. And in this case, they diffuse. And at 1300 degrees K, the diffusion rate is very fast, which corresponds, if you like, to superionic conduction. You see the lattice is vibrating like mad at that temperature. The deuterons are hopping very freely, and the mean square displacement is quite large in these, so it's included.
Lyle Hoppy with Eaton Corporation. Could you extend your work to include the influence or the effect of a transport current to see if that changes the spacing at all?
I haven't thought about that, sorry.
Robert Eagleton from California State Polytechnic, University of Pomona. You mentioned you didn't include quantum mechanical effects in your model, is that right?
That's right, it's strictly classical.
Well, okay, maybe I could make a suggestion. Maybe you might try to put something else in your next model. We all know that, well, I guess most of us know that these deuterons are bosons, and they have a peculiar property of their wave functions tending to pull them into the same quantum state as well as physical space. So you might look into what boson condensation, not only in quantum state, but real space might have upon your model. I just want to make that suggestion.
Thank you.
Of course, that's a very frequent suggestion. And anybody in the audience want to take a minute shot at that?
Well, I am familiar with some of this work, and it's just not clear what the relevance of the Bose gas is to the real situation of hydrogen in metals, where you've got these nice potential wells and things like this. And as I understand the poster that was given by Dr. Bush this morning, which is certainly rather interesting, and it does show an energy minimum, it's not really clear what the value of that energy minimum is. My feeling is that since it must be positive, it's probably a good EV or so above the energy that one has with hydrogen bound in the, quote, normal way in an octahedral site.
One more comment or question?
John Mintmeyer from the Naval Research Lab. More of a comment. I'd just like to say on this previous one about the quantum mechanical effects, we've done some work earlier, about a month ago, that part of it we did embedded atom method calculations, essentially zero temperature optimizations of the structure of the superstoichiometric systems of palladium hydride, PD1 plus X, PDD1 plus X systems, and find essentially the same results. They don't want to get close in the octahedral sites, as Jim Aridin said. We also did some first principles and ab initio cluster calculations, PD6 H2 calculations, and we find the same thing in the octahedral sites using the PD6 as a model. Even with quantum mechanical effects, they still don't want to get close to each other within those. It's the same stuff that I think Peru and that group came out with in a later publication. And it seems to be consistently coming out the same way. The only comment I would make about the boson condensation is it seems those, in my mind, tend to think of these things as non-interacting particles first and then a Coulomb repulsion later, but it really seems the dominant physics of these things at short distances, it has to be the Coulomb repulsion between the deuterons. And that's not going to want these things to be very close. They're going to be a highly correlated system, and they have to be considered such. That's all.
Thank you very much. We'd now like to call for the last paper of this afternoon's session, Conditions leading to the production of cold fusion neutrons by Gajda, Harley, and Rafalski. The paper is being given by Dr. Harley.
Well, good afternoon. This is the last session of a rather long sequence of talks. We seem to have uncovered a trend in the past 3 talks at least, or including this one. That is steadily increasing temperature, steadily decreasing screening length, and steadily increasing levels of pessimism that, in fact, conventional physics can explain the rates that we're trying to achieve. Sorry, is there a pointer here somewhere? This talk is entitled "The Conditions Leading to the Production of Cold Neutrons, of Cold Fusion Neutrons," and what I'm going to be concentrating on in this talk are neutrons, neutron production, that is a rate of 10 to the minus 23 per neutron pair within palladium. This work was done in collaboration with Mariusz Gajda and Jan Rafalski at the University of Arizona. The objective is to explain the production of cold fusion neutrons within the context of conventional physics, coupled with some unconventional process. The particular process that we had in mind was the collapse of cavities. I believe this has been discussed earlier this afternoon. And in the collapse of perhaps cavities within palladium, it may be possible to achieve very high temperatures and pressures for short periods of time, achieve at least lukewarm plasma conditions with temperatures of the order of perhaps 10 electron volts. And would it then be possible, perhaps within another unconventional mechanism such as screening, to achieve the required fusion rates? Let me just begin by defining what I mean by conventional physics. Conventional physics is a system which is in thermal equilibrium. This has already been discussed in the previous two talks. Secondly, we assume that the nucleon-nucleon interaction is essentially Coulombic and is just merely modified in some way by the conditions within the lattice, that is by screening or by perhaps compression from the nucleon sites that was dealt with in some detail by Peter Richards in the previous talk. And these are the sort of systems, situation that we're talking about. And I've listed a couple of the ideas that have come up recently. With electron screening, I think, being established as the most legitimate contender in this regard. And I suppose unconventional physics deserves a mention as well. This includes off-equilibrium processes, exotic behavior, or what it might turn out to be are what I call cosmic accidents. We have no protection really against a very unusual sort of resonance situation occurring. That may be the case. It's merely a matter of time before someone stumbles onto it. But these we do not regard, or I will not regard in this talk as being conventional physics. But we may actually have to resort to one of these possibilities before the day is out. Now, the conventional approach can be incorporated in a very simple model. And I've tried to keep things as simple as possible to just try and convince you that, that the conventional approach is not going to work. That is the conclusion that I'm going to eventually come to. These are two expressions which you've probably seen very often. They're two different equivalent representations of the same problem. To compute the fusion rate, that's lambda E, as a function of energy, is essentially proportional to the magnitude of the wave function, or the probability of the two particles getting close together. This can be written in terms of scattering formalism, and that's the formalism that we used in this particular model. The scattering cross-section is conventionally written in this way, where this S is the cosmological S factor. That has, I'm very glad to see, being computed by Jerry Hale 2 talks ago, and there is actually some discrepancy in the literature as to exactly what the S factors are for the various reactions, and hopefully we'll soon have a definitive table, at least for internal consistency. This eta, or this component over here, is essentially the probability of the wave function being, the amplitude of the wave function of the two nuclei getting close together if you were to scatter them off each other at some finite energy. And in terms of the WKB approximation, what you have is a simple barrier penetration tunneling probability, and you're tunneling through this potential here, VR, through the classically forbidden region. For concreteness, the particular modification to this potential, that the effective potential between the nucleons within the palladium lattice, for concreteness we've decided to look at the screening. This would be an unscreened potential, just essentially 1 over R, and this the screen potential, which has been mentioned earlier, and has this, exponential suppression at intermediate distances, and a bit further out you get things like Friedel oscillations, and so on, but those aren't really relevant in this discussion. This lambda, I've written e to the minus lambda r, is the reciprocal of the screening length. And again, there seems to be some doubt in the literature as to exactly what this value is. We've seen values that range from 0.12 angstrom to as much as 0.5 angstrom. And in fact, we have seen, I think, just about this entire range in the previous 2 presentations. We, however, shall use this lambda as just a method of changing the tunneling potential, which has asymptotically a form 1 upon r, when the nuclei get very close together. No conceivable effect in the lattice will ever modify the short-range Coulombic repulsion. The next thing is the particular reactions we can consider. I think the only reactions that we can realistically consider right now are the various hydrogen reactions. The only two that are missing from here are the PP reaction, which is mediated by the weak force. If you go to very small fusion rates, in fact, that does dominate, because the PP system, of course, has the smallest reduced mass. I think it was Jerry Hale who mentioned this, is the reduced mass in the tunneling integral is very significant for small fusion rates. And I'll show you in another transparency the effect that this has as you change the energy. The second important the second important piece is the cosmological S factor, which appeared in the previous transparency. And you can see this has a range of about 8 orders of magnitude. For Z greater than 1 systems, for right now, we cannot consider those. In the tunneling integral, Z appears, Z scales the potential as Z, and that scales the exponential suppression by Z. And simply, for example, considering helium-hydrogen fusion, you're in a completely different ballpark. If you cannot explain these reactions, you do not have much chance in terms of conventional physics of explaining high Z reactions. So we can go ahead in terms of this prescription and compute cross-sections. Now the reason why I'm showing you this particular graph is just merely to emphasize the two effects that are busy beating against each other. The one is the S factor. If you go to high energies, it is the cosmological S factor that plays the dominant role. And you can see the rates order themselves according to the magnitude of the S factor. As you go down in energy, I should point out this is energy as kV we're talking about. Unfortunately, it's not very well discriminated in this graph. Look at this region over here. You can see that the various rates order themselves according to their reduced mass. And somewhere in between, they've all got a crossover. And they all cross over at about 200 electron volts. This has some rather interesting consequences, which I'll come to in the last transparency. Finally, once we know essentially the interaction strength, or the fusion rate, for each particular energy, we have to know what distribution of energies there are in the system. And this is where we come to our first assumption of conventional physics, that is that the system is thermalized. So we can assume a simple Maxwell-Boltzmann distribution, perform a thermal average for the cross-section times the velocity, and we can obtain a fusion rate. This, as I've defined it here, is the single particle fusion rate to make it directly comparable to, for example, the experiment by Jones. They present the fusion rate for single deuterons within the palladium of 10 to the minus 23 per second. That's the number that we're aiming for in this game. Just one thing that needs to be emphasized. Perhaps I should go back to the previous transparency. When you're performing a thermal average, particularly in the environment of hot plasma, you have two exponentials in your summation, essentially. You have a strongly decreasing exponential resulting from the strongly decreasing probability of occupying a certain state of certain energy. It's all very well to try and compress your two deuterons, put them into the same lattice site, for example, but if that has a higher energy, it's unlikely to be occupied, so you've got to perform the summation of the probability of such a configuration being adopted by the system. So this is the strongly decreasing factor. The second is the strongly generally increasing factor, which comes directly from your tunneling probability. That increases very steeply, and if you multiply those two factors together, what you get is a Gamow peak. This is the increasing cross-section with energy. Here's the energy. Increasing cross-section, decreasing probability of occupation, and the Gamow peak is the product of these two, which I've multiplied by 1,000 because otherwise it would be too small to see. This is a very well-known result in particularly thermonuclear fusion. These are the people who were doing this sort of stuff before cold fusion came around. And the important thing to note is that, in fact, it reaches its peak very high above the temperature at which you're working. This particular calculation, which I've done here, was, for an example, is 5 electron volts. This is sort of approximately 500,000 degrees, a very lukewarm plasma. And you can see that the peak reaches a peak at about 80 electron volts compared to the 5 electron volts, which is the temperature that you're working at. And this is a log scale. If this was a linear scale, this would look essentially like a delta function. So what this essentially means is that your entire fusion amplitude is coming from an energy that is much higher than your temperature. Now, if you're looking for exotic nuclear resonances or something like that, that's something that should be borne in mind. Those resonances are mostly going to be affecting the fusion rate for thermalized systems at energies much higher than the temperature at which you're working. So, having mentioned these points, we can now compute, finally, I beg your pardon, wrong transparency. We can finally compute some fusion rates. This is simply the fusion rate you'd get with no screening whatsoever as a function of temperature. The temperature we've taken is approximately from 1 electron volt to 10 electron volts. It's up to about 100,000 degrees. And this is the fusion rate. And this is the fusion rate that we're aiming for. You can see that for infinite screening length, we are quite a long way away from achieving a rate of 10 to the minus 23, even when all your deuterons are in this temperature of 10 electron volts. As we steadily increase the screening length, however, I'm afraid I think I must have mixed up one of the scales. They don't quite match at the bottom, but that doesn't change the essential results. As you increase the screening length, 0.25 angstroms, 0.1 angstroms, you can see we're gaining a couple of orders of magnitude in the thermalized fusion rate for each decrease in the screening length. Now, 0.1 angstrom for a screening length is very small. I don't think anyone will really accept that as being realistic. But as I mentioned, what we are trying to do is seeing how much we can modify the potential realistically and get a fusion rate which might be somewhere realistic. For this 0.1 angstrom, we do achieve this 10 to the minus 23, but you've got to take into account the fact that only a very small component of your deuterium in the palladium lattice are going to be, if these cavities are collapsing, only a small component of the deuterons are actually going to be in this high temperature phase. So you've got to take into account a suppression of quite a considerable suppression. Yes. So the conclusion we reach for the particular case of a screen potential is that screening is unable to explain, in terms of conventional physics, the observed neutron rates. You have to go to extremely high temperatures to reach these rates, but again, you've got to take into account the suppression. In cold fusion, only a small component of the deuterons are actually at that temperature. And finally, taking these 2 points into account, it is probable that we have to go to one of those unconventional points that I mentioned. We need some resonance, some off-equilibrium behavior to explain even the Jones rate. So that's the final conclusion that we come to. There's just one last observation I'd like to make. I know that was a very opinionated conclusion, but opinionated conclusions have been known to be wrong before. We can play a little game and say, well, maybe this is fiddle and twiddle physics. You have to take a little bit of screening, a little bit of compression, a little bit of this, a little bit of that, and somehow you'll manage to reduce the fusion rate, increase the fusion rate to an acceptable, to the level that we are trying to explain. And what I've done here is played a little game. What I've done is taken the DD rate and normalized that to 1, and then looked at the other relative rates. Remember, in the cross-section, they were all crossing over in the absolute energy of about 500 electron volts, and this is now as a function of temperature. You can see how these various rates correspond to each other compared to the deuteron rate. So if we can observe that, what we can try and do is perform different experiments. We can say, look at the DT reaction, or what would be even easier is look at the PD reaction to gammas. And, well, this involves just diluting your deuterium with a little bit of ordinary water. But if the fusion rates are occurring at low temperatures, you should get vastly more gammas. That's due to the fact of the reduced mass effect. If it's occurring at high temperatures, you should find these rates, the rates are roughly commensurate. And so performing the experiment for PD, PT, DT, and comparing the different rates and seeing, in fact, if these ratios agree for some particular temperature, we might actually be able to learn whether, in fact, this is working very much in a conventional scenario or not. Thank you. That's my conclusion.
Are there any questions or comments for Dr. Harley?
there's one length scale in your problem, which is the screening length, and you set it rather small, 0.1, to get reasonable, rates that you're trying to fit. But that's like putting in the answer by hand. What's the point of this?
I beg your pardon?
What's the point of all this? You know that if you change the scale lengths, that you get a molecular deuterium, which is about typical mean distance of 0.7 to 0.1, you're going to increase the rates in a fabulous amount because of the rapid variation of the Coulomb barrier penetration. But you don't have to do any calculations. That's well known.
Of course, but now it's established. It is well known, of course, that you can change the rates to a very great degree when the fusion rates are very small. The object of this exercise is to try and change in some way the tunneling barrier, the tunneling probability, the tunneling potential, and see if such rates can be achieved or not within the possible modifications that can come from the electrons within the lattice. That was the objective of the exercise. And it seems that the answer that fusion can be achieved simply by modifying the tunneling potential is not. It is not possible. Thank you.
Somebody here has a list of the speakers. Somebody here has a list of the speakers who've been approved for the first section of the discussion group tonight. It would be interesting to see those, I think.
I'm going to help them prepare highlights of the workshop. Okay, you better go to.
And now, while we're looking at a map of how to get to the El Dorado Hotel, I hope you'll join me in thanking the speakers of this afternoon's session.
Nuclear fusion, it's what powers the sun. Cold fusion, it creates headlines, and some say it could power Earth's future energy needs. Indeed, 2 months have passed since researchers called a press conference at the University of Utah to announce that they had demonstrated cold fusion. Controlled nuclear fusion, that is, at room temperature, achieved on a tabletop in an electrochemical cell, a test cell containing the metals palladium and platinum immersed in heavy water. Now, scientists from around the world are in Santa Fe, New Mexico. They've come to this, the oldest capital city in the country, a city tucked at the base of the Rocky Mountains and located in a state renowned for its unique blend of culture and cutting-edge science and technology. They're here for a special workshop, the Workshop on Cold Fusion Phenomena, an event sponsored by Los Alamos National Laboratory under the auspices of the U.S. Department of Energy. There are data and ideas to share and discuss, and research directions to chart and clarify. This satellite broadcast is available anywhere in the continental United States. Join us now as the proceedings continue. Let's go live to the Sweeney Convention Center.
It's 8 o'clock. I'm standing in for Fred Morse, who's had a delay this morning. As we're getting started, I'd like to turn the podium over to Dr. Hackerman for a few remarks.
Will the late breakfast eaters please sit down? I simply want to make the point to you that the discussion tonight will be fully open. There'll be no papers to be presented. I would like to ask the speakers to be sure to be here this evening so that questions can be put to them directly by others in the audience. I would like to ask those of you in the audience who have something that they want to comment on, not to have happen to have a handful of slides in your pocket. In order for everybody to get a chance to put their questions, which are seriously meant and seriously used, be as pithy and terse as you can. And I suspect that if necessary, and if the setting is proper, the 9:30 closing time is not all that firm, so that all of the questions and responses can be had. I've been asked to tell you that Garland put a pile of these reprints of Consensus on Cold Fusion, Still Elusive, out of the April 20th Nature on that table in the back there where the young man is sitting. Read.
Thank you. There have been a few changes in the agenda for today, both because of cancellations and other items. So I'd like to show you what we have in mind right now, if you'd show us the first slide. We'll start off with a series of 3 talks involving neutron measurements from metal systems. And we would like to run this in a mode that each one of these speakers gets their allotted time, and then we'll hold the questions on these 3 talks to the end of the 3 talks, and so we'll have a period of 20 minutes for questions at the end. Show us the next view graph, please. These 3 are related. Then after that, we'll follow with the talk from Scaramucci from Frascati, Dr. Guy, and then we'll have our break. Then the talk from Princeton, and so forth. And this shows the program down to our lunch period. I wanted to ask, before we get started, is Dr. De Maria in the audience this morning? Would you, if anyone sees Dr. De Maria, if you'd have him get in contact with me, I'd appreciate it. Without further ado, then, we'll make time available for the first talk by Dr. Steve Jones from BYU, the title of which is Cold Nuclear Fusion and Condensed Matter, Recent Results and Open Questions. This is an invited talk, so he'll have 20 minutes.
My voice isn't that strong, so it's coming. It's coming. Here we go. We're on. Okay, neutrons are very weak, as you know. I told my sister, I've been working at Los Alamos, for the past several weeks, sort of commuting to Los Alamos. And I told my sister that we had some neat results to report this morning. And she said, did you say heat results? And I said, no, not heat results, neat results. So I'll clarify that at the outset. I want to trace real briefly, and it's going to have to be brief because of time, a little bit of the history of our research at Brigham Young University in this field of cold fusion. It really began in 1985 when it became clear that muon catalyzed fusion, which I've been studying for some years, as very interesting as it was, had some fundamental difficulties, which we're still studying, by the way. The alpha muon sticking, some of you have heard about. But I suggested to a friend, Clint Van Sicklen, that perhaps we should look at some other techniques. Would it be possible, for example, to induce fusion at room temperature, let's see, room temperature, by increasing the density of deuterium molecules. Where are we? Deuterium's in there somewhere. And we wrote a little study on this, and 4 years ago. And then we looked at the possibility of metallic solids, that is metallic hydrogen. A fictional binding particle of twice the muon mass would lead to fusion rates, reasonable and interesting rates. We didn't know how to do this, of course. But I think I'll show you. This is basically what we talked about in our paper. Looking at fusion rates in an ordinary molecule, this has been discussed already. Fusion rate is about 10 to the minus 70th per second. If one replaces an electron in the molecule, or two electrons with a muon, so we have muonic binding here, the distance between the nuclei decreases by a factor of about 200, which is the ratio of the muon to electron masses. Then the fusion rate increases by 80 orders of magnitude. This is a very dramatic effect. A less severe but a very interesting possibility is that a quasi-particle somehow of mass a few times that of the electron could reduce the separation and lead to fusion rates we calculated about 10 to the minus 23rd per second. This paper, Journal of Physics G, was published in March of '86, and in that month I gave a talk at Brigham Young University on cold fusion, including muon catalyzed fusion, and this new topic, this piezonuclear fusion we call it, somehow squeezing the molecules together. Now, at the talk, I should give special credit to Paul Palmer, professor at Brigham Young University. He was aware of these data here that I'm showing. That is, that in hot places of the Earth, in particular volcanoes, there's anomalous amounts of helium-3. So the helium-3 to helium-4 ratio, for instance, in Hawaii is about 10 to the minus 5th, whereas in continental crustal materials, it's about 10 to the minus 8th, about 3 orders of magnitude. And this combination of ideas, the piezonuclear fusion concept with this enormous excess of helium-3 in essentially all hot spots, geothermal areas of the Earth, led Paul to conclude that perhaps we have geological cold fusion. And that was our start into this field, independent of any work elsewhere in 1986, March. So the idea is then that somehow deuterated water is carried along with, this happens, it's well known actually, carried along with a subducting zone. So as the plate tectonics works, you carry water along with the minerals deep into the Earth where partial melting occurs. And then it's possible that these types of fusion reactions can occur in the Earth. PD giving you helium-3, DD giving you helium-3 again, and roughly half the time a triton, but tritium decays into helium-3. So this would account for some interesting excess helium-3 in the Earth. We discussed this immediately with Harmon Craig, University of San Diego, Scripps actually, and or both, I guess. And Harmon thought it was a reasonable idea. He was really the one about 10 years ago who noticed these enormous excesses of helium-3. And so he thought this was a reasonable idea. Let me just show you. Paul Palmer keeps a beautiful logbook talking about our colloquium, and then this is the idea. Perhaps somehow the rock catalyzes the reaction. Oxygen might catalyze. March 13th of '86, he talks about this. And we did some calculations very quickly and decided that this is in our paper in Nature. By the way, let me pause briefly on that. Those of you who have read the preprint, which is quite a few, I suppose, might not have taken time to read the Nature paper. Now, the peer review process is a wonderful thing, as you know. And we went through that and changed the paper a fair amount. And I'd encourage you to read it because there's some good stuff I think you'll find in there. We did cut down quite a bit on the geological section because the Nature editors asked us to shorten the paper. Doesn't mean we disbelieve the good stuff on geological fusion. It's just we had to cut it down. Anyway, the point is that we calculated that fusion rates at about 10 to the minus 24th per deuteron per second could account for the helium-3 flux measured by Harman Craig and others coming from the Earth. This is a sort of a global flux, right? And at this rate, cold fusion, if we could reproduce it in the laboratory, we could detect fusion at that rate. So we pursued that. Very exciting day, April 7th. Jan Rafalski, I'm sure, remembers it. He came to BYU and we had this brainstorming session where we looked at this process, electron-catalyzed fusion, we called it, and we looked at various metals like palladium and platinum, aluminum, nickel, so on, lithium is here too. We talked about, this is very important, the guiding principle, non-equilibrium conditions. We talk about shocking the hydride, heat, vibration. This is '86, okay? We outlined what we were going to do for the next few years. We took some measurements, in fact, we started with electrolysis, May 22nd, our first experiment. And how are you going to get hydrogen into metals? Well, electrolysis is one of the easiest ways. This picture has recently appeared in a little different form on the cover of Time magazine and so on. But the point is, once you get this idea, which we did get in '86 independently, as I said, of any other work, then the electrolysis cell from that point is going to look similar to other electrolysis cells, right? Electrolysis happens to be one way of getting hydrogen into metals, deuterium in this case. We did use other ways, however. And in particular, we have used the pressure loading method, also used it in Italy. We started that back in '86 as well. But we never cooled the pressure loaded samples. We only dealt with higher temperatures. So my hat's off to Professor Scaramuzzi for trying that. Now, we saw fusions, we thought, perhaps at a small level. But we realized if we were going to believe our results of the summer of '86, we worked pretty hard, we would really have to refine our neutron counter. It's not easy. We didn't see a lot of neutrons, right? So it's clear that we had to work pretty hard. And we developed then a program. We started a program to develop a neutron counter. This is a picture of Bart Zier, the principal neutron counter man, expert. And you see inside this neutron counter now the two photomultiplier tubes. A schematic of the counter and of the experiment looks like this. Now, I would really like to get on with the new results rather than spending a lot of time on the published results. So I will encourage you then to read in Nature, and I'll talk very briefly about our current results, okay? Because I really like to get on to the present stuff. Now, the idea of this spectrometer is that if a neutron is produced by this means, for example, DD fusion, it will enter the active volume of our counter where collisions with protons in the liquid scintillator will occur, giving recoil protons. About 6 collisions slows the neutron down enough so that it can be captured in the lithium-6 doped glass. Lithium-6 captures, so you get a reaction N plus lithium-6, giving you a triton. The proton, this gives you a scintillation of a pulse width about 70 nanoseconds in the glass. Now, the pulse width of the recoil protons in the liquid scintillator is about, well, it's a few nanoseconds. So we can easily distinguish by pulse shape analysis, the signals in the liquid as opposed to the glass. We require a coincidence between liquid and glass. Very important point. And we gather up then the energy, the light output, which represents the energy, from all the collisions in the liquid scintillator, and that gives us a handle on the energy of the neutron. It's very important to us to identify that these are 2.5 MeV neutrons so that we can tell whether or not we have fusion, since the fusion reaction results in a characteristic neutron energy. Here's a picture of our apparatus. The blue box is the neutron counter. I'll show you. Well, and the little cells here are the electrochemical cells. We calibrated our detector. It took us several, if you look back, man-years to develop this counter to the point where we could believe it, calibrations and tests and so on. But I'd like to point out on this calibration that a 5.2 MeV neutron that has a head-on collision with a proton in the liquid scintillator results in you see from the shoulder, you can identify these are 5.2 MeV neutrons. Now the response of the detector, and these are, of course, are 5.2 MeV protons because head-on collision, but the response of the detector is nonlinear. So as we get more collisions, it spreads out the energy. The more collisions you have, the less the apparent energy of the neutron. So you get this type of a distribution like this, and the width we measure is not great, but 50%-ish, and we're working on some, Bart Zier is working on some other materials, some inorganic hydrogen-rich materials, which should help us improve this, but that's another story. So we looked at 2.9 MeV again. This shoulder is well defined, and actually the shoulder, the spacing is linear. We checked that. And so we know exactly where the shoulder occurs for the 2.5 MeV neutrons, and we know the width based on these other calibrations. So we really know where to look for 2.5 MeV neutrons. Okay? We do that, and the background looks like this. Talk about backgrounds a little more, how we do it. Fairly smooth distribution. This is energy and counts along the vertical. And if you superimpose then the data, all the data we collected in essentially January, February of this year, some going back into last December and so on. Anyway, you see an excess in the region of where we expect to see 2.5 MeV neutrons. Channels 45 to 150, there's an excess of counts. So you subtract scaled background, you see about 170 excess counts in the region which we have identified by the calibration. It's 2.5 MeV neutrons. And sigma is calculated in the standard way, square root of the foreground plus the background. Background is multiplied times the scaling factor squared. We took about a little over twice as much background as foreground data. This is one way to analyze the data. And the technique is explained in some detail in the paper. Another way, so the significance is about 5.7 sigma if you do it that way. I think you can see the peak there. And actually, when I first did this subtraction, I guess it was in February, I asked my son, do you see a peak in there somewhere? And he said, I think so. And but for the paper, we decided to present this in this fashion, a little less striking perhaps, but then we also analyzed the data by doing a Gaussian fit to this peak, another way to estimate the statistical significance. The amplitude of the peak is 23.2 plus or minus 4.5 counts. Again, a little over 5 standard deviations. This particular analysis was done by Al Anderson, Idaho Research. We've also analyzed this significance another way, which I think is the best way, looking at rates. This is in our latest version of the paper. I'm getting to sound like a broken record here, but please look at that. we look in the channels of interest and we see a statistically significant difference in rates. Now we're normalizing not by counts in some region of interest, but rather by the duration of the runs, foreground to background. We simply take the counts divided by the duration of the run, and that gives us a rate. And as a check, now we're not specifically trying to make the high energy region match up here, okay? It's a difference. We're normalizing by rates, but there's a check. We look at the high energy background rate to make sure it's the same, and it is, okay? Please read the paper. But you see, again, the significance, this is just a subset of the data, but the significance already approaches 5 sigma by this method. If we plot the neutron source rate as a function of run number, as opposed to plotting foreground to background ratio, I prefer this way actually of plotting things. We see that there are some statistically significant deviations in the rate, which are not well understood. We can't predict at what rate, when we set up our cells, we're going to see neutrons. But fairly consistently, you see, we do see a neutron signal. The average rate turns out for the first 8 runs to be about 0.06 neutrons per second. And I think rather than comparing with the maximum rate, which is 0.4 neutrons per second, this source rate now, production rate, it's probably better to compare with our average rate. Obviously, we haven't seen before or since a run like that, which is by itself nearly 5 standard deviations above the background rate. But I must admit that if we hadn't seen that run, we probably would not have published what we did. All right. Could the 2.5 MeV neutron signal be artificial? The answer is yes. And we've tried to check a number of possibilities and rule these out. And again, time is very limited. Let me just emphasize that we've looked at zero current cells with heavy water. These are featureless. We've looked at light water cells, light water control experiments, prior to publishing our Nature paper, in case you were wondering. We did do a number of those. Yeah. Some of you may have noticed Dr. Maddox thought we hadn't done that and criticized us thoroughly for not doing it, but we did do it. I don't know how he got that idea. It's in our original preprint. And we did cells, let's see, background runs short, long, different times of the day. Finally, this question of muon catalyzed fusion, I think, can be pretty well ruled out by experiments that have been done. We'll hear about another one today. And by the fact that in the Grand Sasso lab, experiments were done where the muon catalyzed fusion possibility is essentially eliminated. The cosmic ray background is extremely low in the Grand Sasso tunnel. The backgrounds look like this. They're featureless. This discussion of how we came up with this Mother Earth soup for our electrolyte is discussed in the paper. And essentially, it comes from our geochemical considerations. And we mentioned the fact that there's a lot to do to disentangle the various parameters that can affect the rate. Recently, however, we've simplified the electrolyte. We're using primarily lately just a little bit of palladium chloride, lithium chloride, and still the acidic solution. We still see neutrons at BYU. Average rate is coming in at about 0.04 neutrons per second recently. At the BYU Bologna group, I should turn that around, sorry. Bologna BYU group. These data will be presented by Dr. Bertin, coming right up. So I will not discuss those much. Los Alamos BYU, look, if you've done a little experiment, right, and all of a sudden you get all this publicity, which you weren't expecting. So what do you do? Well, what I did, besides talking about, which was sort of required of me, what was going on, I tried to get some experiments going to check myself as fast as I could. Now for us, these experiments, things keep turning up roses. You might catch a little, not trees, but roses, you know. Anyway, these results will be presented here as we go along. And it's been fun. I want to talk a little about the Los Alamos data, not the pressure loading stuff, which Howard Mallove will discuss, but a little bit on the electrolytic infusion experiment. This is a picture of the apparatus. We're using helium-3 proportional counters here. The overall efficiency of this setup is about 17% for this configuration. 6 electrochemical cells. I'll talk a little more about the electrolyte in a minute. Some of you might want to try doing this sort of thing. The results were interesting here. Let me say that it led me to an appreciation of the difficulty of trying to measure neutrons at this rate. This is our first effort, and April 28th, the background level is shown here. We didn't, I don't know, this is not much to write home about, folks, but there's probably something there lasting of the order of 8 hours. We ran again, and I haven't tried to regroup these data. These are 1,000 seconds per point here, 1,000-second durations for each run. This is the cycles per second, so the rate. You see the background level is 0.37 or something like that, 0.37 neutrons per second. Now, if you look here at the another run, this turns out, and here I've grouped things in about 4,000 seconds per bin, and you really okay. I'll keep it right short. Thanks. Whew. Look, I think this is about 3 sigma. Neutron rate is about 0.08, but it's clear that it's difficult to see a signal with this type of a background encounter. We've improved things since then, tried to. But I want to point out it takes a very sensitive neutron counter. Minutes, yes, well, okay. We did see some bursts. This was very interesting. And I'm going to leave it to Howard Mallove to explain how the electronics is done. Very unique system, I believe. Very unique, yes, qualifying a superlative there. But anyway, we do see burst events in the electrolytic cells. All of a sudden, neutrons, about 53 in this case, within about 128 microseconds. We've seen that several times. The detector ran for weeks with somebody else's types of cells without seeing any bursts. We saw bursts after the current was turned off, but we did not see bursts after the cells were removed. After the current was turned off, there's still a lot of deuterium, and it's moving, it's still sitting in the heavy water. Okay, oh boy. I'm going to have, if anybody would like to know how to see cold fusion neutrons, you're all set up. I will talk about this in question-answer period, I guess, or tonight. Here's a picture of our pressure loading scheme, independently looked at by Scaramucci and others. Look, I think the most important thing, and I really want to home in on this, is looking at the rates. This was gathered, now here I'm plotting orders of magnitude along the vertical scale, and just a bunch of experiments gathered from the APS meeting. Here's break-even somewhere up in here, Pons-Fleischmann neutrons here. And then the red results are claims of neutrons at this level, which happens to be about the BYU level. Green are upper limits, not seeing neutrons. From yesterday, I add a few more. Wolf's data from Texas A&M looks about the same as this level that we reported, as well as Mallove, as you'll see in a minute, from Los Alamos weighing in, with the randoms rate at about the same level. I think it's important that we discuss rates and not simply, I saw neutrons, ergo, cold fusion is going to be the power source of the future, okay? Well, we really got to be a little more scientific and quantitative than that. I've put down here, these are a little bit estimated, the helium-3, helium-4 rates from Texas A&M, and the tritium rates, which I believe is still down by orders of magnitude. If I understand, you saw the plot, it builds up over time. It takes time to get that tritium in there. I used a few days to get this. And yeah, I may be off by an order of magnitude or two, but I don't see how you can get a correlation between heat and tritium from the data presented yesterday. Also, frankly, well, let me make this is a quotation from Nature. There's a couple things going on here, and I received a letter dated May 15th asking me to, this is a major laboratory in the United States, asking me to please send some of my cells that were producing excess heat. And I was a little shocked. You put 1 watt into our cells, you lose a watt. I mean, you get a few neutrons, right? But no excess heat, okay? Let's see if we can get that. There's different things going on here, okay? They're separate, independent experiments, I'd like to follow Dr. Who was it? MIT Stan Lockhart last night. Let's go through and see, which reaction rates. I don't have a whole lot of time, but 3 helium is out because the guys have measured it now at Texas A&M. 4 helium's out. Look at that. They go away. Beryllium-7 you can have if you want, but it's endothermic, and so it won't help you much on the excess heat. The only one left is perhaps the tritium. I'll tell you, we've measured, muon catalyzed fusion, muon catalyzers have measured this branching ratio, and it favors the helium-3 branch a little bit. This was also mentioned, and I thought there was an elegant R-matrix formalism. Remember yesterday, Jerry Hale, Los Alamos? He got the same branching ratio, folks. This is solid. I mean, I don't know, you might be able to argue away a little bit, but 8 orders of magnitude branching ratio, I don't think so. Really don't know. I think we have to, and also, if you see helium-3, you should be able to see some tritium decaying into helium-3 too. So I don't really think that that's an avenue for an explanation of the excess heat. I think the low neutron rates, the low rates that we're seeing actually challenge very strongly these notions that the excess heat observed in the Pons-Fleischmann experiment are due to fusion. Very strongly challenge that. However, I do think that there is a cold fusion phenomenon at very low rates. There's a possibility of 2 explanations. I won't have much time to discuss these. Piezonuclear fusion or fractofusion. Apologize again. Fractofusion has been looked at very hard at Los Alamos. Okay. And here it is. We're going to be doing some work at Los Alamos with this nice BGO, bismuth germanate detector, using primarily the pressure-loaded system. And we hope to see if there are any gammas from PD fusion from this technique. So, skipping right to my conclusions. Yeah, time flies when you're having fun. We think we're seeing fusion at a low rate, 7 sigma level at Gran Sasso, and the pressure loading method about 11 sigma. This is now the random event rate. The bursts are much higher in statistical significance than that. Fusion rate's low, no energy. Reminder, please tell us your rates. And these are coupled, incidentally, the neutrons and the tritium, I believe. I don't see how I can get out of that, folks. However, I do think there's an interesting phenomenon here which could relate to geophysics, a probe of extreme conditions in metal hydrogen systems. And I think we'll have some fun studying this. This is this rose I talked about, which involves a number of disciplines. And if we work together, I think we can understand this. Thank you.
According to Steve's own request, we'll move right along to the next paper, the title of which is Experimental Evidence for Cold Nuclear Fusion and a Measurement under the Gran Sasso Massif. And the authors here are Bertin, Bruschi, Capone, De Castro, Marconi, Moroni, Piccinini, Semprini, Cesario, Trombini, Vitali, Zoccoli, all from the Italian Institute of Nuclear Physics, and also Bart Zur, Jensen, Jones, Palmer from BYU. The speaker is Dr. Bertin.
The report was prepared by Antonio Vital and myself and is presented here on behalf of the Bologna and Brigham Young groups who are collaborating at the Gran Sasso Laboratory in Italy. The report concerns the preliminary results we obtained on the neutrons released following the electrolytic infusion of deuterons into titanium electrodes. The measurements were carried out searching for 2.5 MeV neutrons, such as those released in the nuclear fusion reactions of 2 deuterons. The first objective of the group is to observe the effect recently found by Jones and colleagues under privileged conditions of neutron background and with a different apparatus. With this in mind, we are performing an experiment which is based on the following points. First, to carry out the measurements at the INFN Gran Sasso Laboratory This laboratory is situated about 120 kilometers from Rome in the proximity of one of the longest European superhighway tunnels. Entering from the Aquila side, the rock shield progressively increased, attaining more than 1,400 meters in correspondence of Mount Aquila. In this position, the three underground laboratories A, B, and C were bored. The experimental halls are about 20 meters high, 100 meters long, 18 meters wide approximately. The natural radioactivity level is about 10 times smaller than the usual one, while a 4,000 meter water thickness equivalent provides an exceptional natural shield with respect to cosmic radiation. Apart from neutrinos, only a few high energy muons are left through this shield, with a flux millions of times smaller than the one measured at sea level. Second point, to use proton recoil liquid scintillators as neutron detectors, which allow to reduce the gamma ray background by means of established neutron minus gamma pulse shape discrimination techniques. The neutron minus gamma discrimination was obtained by the method of gating separately the fast and slow component. Fast will be called energy in general, and slow T, tail, T stands for tail, component of the same scintillation curve. It is seen here the integrated form of two scintillation pulses due to gamma rays and protons respectively. In this case, neutrons and gamma rays distribute them on different regions in a two-dimensional display of the energy versus tail plot. When we shall speak of a T-cut in what follows, a T-cut on the tails, it will mean that we are referring to a horizontal cut on this figure. Third point, we perform simultaneous measurements in two equal detectors, a detector called counter A, where the neutron emission is to be observed, and counter B, which is set in a remote position distant from the cells, and monitor the background counts. Fourth point, we decided to use the same mixture of gas salts adopted by Jones and collaborators while preparing the electrolytic solution with a D2O, in order to keep fixed this parameter. For those we might improperly call historical reasons, however, an almost double proportion of salts in D2O was used so far in the measurements. The results presented in this report were obtained during preliminary runs in which the neutron counters were not fully optimized with regard to the neutrons minus gamma discrimination and were operated with minor additional shieldings within the Gran Sasso Laboratory Hall C. The electrolytic cells were 6 centimeters high, 4 centimeters in diameter glass containers. Gold foils having a thickness smaller than 250 microns were used as positive electrodes. The negative ones were fused titanium pellets about 1 gram in weight. The electrodes were kept at a distance of 2.5 centimeters from one another. The DC power supply provided 6 to 10 volt with currents of 40 to 60 milliamps across each cell. 3 cells were operated simultaneously. The neutron counters were made of Ne213 liquid contained in cylindrical glass cells 5 centimeters thick and 12.5 centimeters in diameter. The neutron minus gamma two-dimensional discrimination figures were established initially, as in the figure which I showed you previously, by means of an americium beryllium source. The energy calibrations were obtained by sodium-22 and cesium-137 sources. The energy resolution of the neutron detectors was about 28% at 0.77 MeV electron equivalent energies. The neutron energy scale was determined on the basis of measured electron to proton energy response curves. This response, which was measured by Vitale, Placci, and myself for Ne213 cells of comparable size to the present ones, turned out to be very similar to the ones given by the supplying firm for the presently used detectors. For the present purposes, the most significant background under the Gran Sasso tunnel in whole sea turned out to be the gamma activity. Although much less important than the one recorded by our counters in Bologna, this gave a counting rate within the same detectors of the order of 3.5 10 to the fourth counts per hour, when a lower energy cut at 0.16 MeV, electron equivalent energy, was operated, without any discrimination on the neutron minus gamma plot. This rate is consistent with the ones measured under the Gran Sasso group by other authors with different detectors. The efficiency of the gamma discrimination procedure is obviously bound to the cut operated on the tail axis. Measurements in Bologna with gamma sources proved that our rejection power was better than 1 to over 10 to the fourth at the highest cut operated on the tail in our runs, and for a lower energy cut of 0.3 MeV electron equivalent energy. In this condition, background measurements under the Gran Sasso laboratory provided a counting rate close to 10 counts per hour, which was consistent both with the 1 over 10 to the 4 gamma ray rejection efficiency and with a very small neutron background between 5 and 10 counts per hour, in agreement with previous results by Fiorini and by Belli. Under these conditions, a neutron emission rate of the order of the one reported by Jones and collaborator was expected to be clearly detectable with our counters. Now let's come to the measurements. The cells were kept in front of counter A. Counter B was kept about 8 meters apart from A. Background measurements were performed before and after operating the cells in both counters. The neutron minus gamma discrimination threshold was set at the level fixed by the previous calibrations for the online analysis. The measurements were carried out in subsequent runs of about 1 hour each. After about 1 hour following the connection of the cells to the power supply, the counting rate of neutrons, defined in this way, markedly increased, went through a maximum, and eventually dropped in about 3 hours at the level of the background counts. This behavior was observed in 2 subsequent sets of measurements. The neutron counting rate in detector A fell at the background level when the cells were removed, while the rate of signals was close to its maximum. Counter B, to which the cells were then approached, recorded a significant signal increase. In the next slide, the behavior described is shown as obtained offline after subtraction of the background. Runs 14 and 21 were performed before and after operating the cells. Runs 17 to 20 correspond to the period where the cells were operating, and from runs 17 to 19 one sees that detector A records a significant signal-to-noise increase, which disappears during run 20, while the cells were still under operation. In the upper part of the figure, it is seen that when the neutron minus gamma cut is kept low at this level, and a significant contamination of gamma rays is included within the accepted events, the signal is insignificant. On the other hand, it is seen that when the tail cut is increased, going to these levels of cut, these figures correspond to increasing level of tail cut on our neutron detectors, a significant signal appears, which obviously decreases while increasing further the tail cut on our events. In the lower part of the figure, the corresponding behavior of detector B is shown for tail cuts operated with the same criterion as above. It is seen that no comparable signal is in runs 17 to 19 is present in the remote detector B. This behavior was confirmed during the second set of measurements. The total number of collected neutrons for a lower energy cut of 0.3 MeV was 350, with an error of 51. As a second step, we analyzed the energy spectrum of these neutrons by looking at the distribution of the relevant amplitude signals. The results obtained after background subtraction are presented in this transparency, where they are compared to the Monte Carlo calculated amplitude spectrum for 2.5 MeV neutrons impinging on our detector. The calculation took into account the geometry of the detector, its observed energy resolution, and the quoted energy response curve of the Ne213 liquid to electrons and protons. We conclude that the observed energy spectrum within experimental errors is compatible with 2.5 MeV neutrons, and we interpret these results as the evidence of the emission of 2.5 MeV neutrons by the cells during their operation. On the basis of the Monte Carlo calculation and of the calibrations performed, the overall efficiency of our counter turned out to be 4 plus or minus 0.6 10 to the minus 2 for 2.5 MeV neutrons, when a low energy cut was operated at 0.3 MeV electron equivalent energy, which is the energy cut operated on the amplitude spectrum. This number includes a solid angle of about 25 10 to the minus 2, with which the cells were viewed by the detector. Keeping into account that the neutrons collected were obtained during a total cell operation period of about 10 hours, this would correspond to an observed neutron emission of about 900 neutrons per hour. In order to compare it to the maximum one, about 1,500 neutrons per hour reported by Jones and collaborators, the following points of difference should be recorded between the present and the previous experiment. Typically, 4 cells having characteristics similar to ours were used in the past, to be compared to 3 in the present work. Scaled up for a factor 4/3, our observed neutron emission becomes of about 1,200 neutrons per hour. Other point, we used, as mentioned, a double proportion of metal-salt mixture with respect to the previous work. And the measuring time interval during which we observe a detectable effect in connection to the operation of a set of cells is smaller by a factor of about 5/8 with respect to the corresponding time, which was evidenced out by Jones et al. We have about 5 hours working cycle with respect to 8 hours. Keeping in mind these differences, and the fact that some of them may be connected to each other, and also that the quoted rate of 1,500 neutrons per hour corresponds to the optimal performance of the previous apparatus by Jones and collaborators, we should like to formulate the following conclusions. The present result confirmed the emission of 2.5 MeV neutrons following the electrolytic infusion of deuterons into titanium electrodes. At the present status of our knowledge, keeping also in mind that no neutrons were observed above 2.5 MeV in our spectrum, the only reasonable explanation we see for this fact is that reaction 1 is actually catalyzed when deuterons, reaction 1 is the fusion of 2 deuterons within our electrodes, is actually catalyzed when deuterons are made to diffuse up to titanium electrodes. We consider then the present results as further evidence of the occurrence of cold nuclear fusion in metals. The rate of observed neutron is of the order of the one previously observed by Jones and collaborators. Under this respect, their experiment is confirmed by the present measurement, with a statistics which is more than twice and an entirely different detection system. It is confirmed that electrochemistry plays in this type of measurements a quite significant and critical role. At present, we are preparing new measurements. The present results indicated us that the apparatus has to be optimized, both as far as regards the detector performances and by further reducing the gamma background by adequate shielding procedures. We also wish to perform more systematic blind measurements to achieve more statistics and to carry out extensive reproducibility tests, which we had not the time to do since we felt the urgency of looking directly in the offline analysis into these results. However, the fact itself that the small neutron emission effect was detected in the Gran Sasso laboratory under the conditions described seems to us quite significant. Besides the quoted systematic improvements, an appealing goals of the next measurement would certainly be to observe gamma rays from PD fusion, which have an energy at which the gamma background at Gran Sasso is impressively 0. No counts at 5 MeV. Thank you. Is there discussion?
We'll take the discussion for this paper along with the previous one and the one that we're about to announce now. This paper is the measurement of neutron emission from titanium plus D2 gas. The authors are Howard Mallove, M.M. Fowler, E. Garcia, A. Meyer, M.C. Miller, and R.R. Ryan from Los Alamos, and S.E. Jones from BYU. The speaker will be Howard Mallove.
Thank you. Sometimes major scientific breakthroughs are made by accident with experimentalists, and this morning when I was getting out of the shower, I looked in my hand and I had my tube of woolite instead of shampoo, and so I'm waiting for those results to come in. Reed Jensen's collaborating with me. Because it's no one's ever seen a neutron, we found it convenient to give a mental image so that we can talk some about the characteristics of neutrons with a better visual image. And there's been a joke around the laboratory that we're looking for ducks, and so these are some priorities that one should have when looking for ducks. The first one is sensitivity. Are there any? When do they come and go? The time history. How fast are they? Do they arrive in flocks? Are there bursts and pulses? And what's the absolute yield? In our experiments at Los Alamos, we have found all these characteristics except number 3, and we still are working with yields that are too low for our equipment to bring out the energy. I'm going to talk about 2 different kinds of neutron events. One event is what we call random emission, and that means the neutrons come out with no time correlation to each other, like a radioactive random decay. On the other hand, we're also going to talk about bursts of neutrons that come out time correlated with each other. The equipment that we're using is a class of detectors. We actually have 4 different detectors in the experiment, and this is typical of the detectors, which are high efficiency helium-3 tubes in polyethylene. This particular detector has 16 tubes in a small annular polyethylene body. We're putting the samples in the center of the detector to give very good geometric coupling. So the total efficiency of this detector is 34%. On the electronics of the detector, we've employed some neutron amplifier, preamplifier, and discriminators that are located in the top base of the detector tubes that therefore we can shield them in cavities that are sealed hermetically against moisture and sealed to prevent RF penetration. So they're very noise resistant. For instance, we can put a noise generator like a testicoil in the sample position and not pick up any noise from it. Environmental tests that we've put the detectors through include gamma ray sources at the sample position up to 1 hour per hour with no counts. temperature cycling with a coefficient of 0.01% per degree C. I already mentioned the electrical noise. Microphonic noise, we've done many tests and show we don't pick up microphonics. And the stability over a period of a month is 0.01% using a constant source. This is a picture of the complete system, which has the detector body that I've described, and then the electronics. The time correlation electronics is packaged in a very compact package for portable applications. We've been using this in nuclear safeguards field work, but it does the time correlation counting. Unfortunately, my time this morning doesn't permit me to describe that in detail. In our experimental room, we're located three floors underground with a heavy concrete shield overhead, about 1 meter thick. And we have 4 detectors operating continuously, located at 1 to 2 meters from each other. System 1 is the one that Steve Jones showed the electrolysis cells running in. System 2 is a simple annular counter. System 3 also has an exterior ring of helium tubes that act as a crude energy spectrometer should we get enough yield. System 4 is what I just showed you. All of those systems range from 19 to 34% efficiency. This is an example of what I had as System 3 in my previous slide. Most of the results I'll report relate to pressurized gas cylinder, of which this is an example. So they're about 25 centimeters long, 2 centimeters in diameter. This detector has the exterior tubes that have the function both as a spectrometer when we have sufficient yield, and they also serve the function as a control detector when you're in the low mode. That is, if you can tell whether a neutron originated in the room or in the center of the counter by the ratio of the inside to outside rings. When we put the first cylinder into the counter under the pressurized gas system, we observed our first significant event, and it was observed on top of this detector. It was a genuine observation that other people haven't seen yet. Then later in the experiments, we found a similar one in the channel counter. So we knew we were getting results at this point. We also had an X-ray detector looking at the samples in the counter as well as the neutron system. In this location, we might have gotten more results with a tritium sniffer. Our management said that before we ought to present our results, we should get our ducks in a row, so this was that one. Our data controls for these experiments were at least 2 similar counters adjacent to the primary counter operating during the entire experimental period. That gives us a feel as to what the environment was doing. We had a dummy cylinder that was run through the same cycling as the active cylinder intermittently with the active cylinders. Environmental chamber test, and also our counters had been operating for more than a month looking at the electrolysis experiments with none of the burst effects that I'll describe shortly. For the gas phase experiments, this is a diagram of our sample. We would fill the sample with approximately 100 grams of titanium metal in different forms. In some cases, palladium was mixed with the titanium. Then the material was outgassed and then backfilled with 40 atmospheres of deuterium gas. We would see no neutrons until we put the system through an experimental sequence. The sequence was to load the deuterium in a separate building, seal the bottle, take the bottle to the laboratory, and put it in a liquid nitrogen bath. After about 10 to 30 minutes, the cylinder had come to liquid nitrogen temperature. Then we remove it from the bath and put it in the neutron detector and let it warm up. Because of the mass of metal in the cylinder, mainly the cylinder itself,